3.6 Model direct variation. Direct variation means two variables x and y show direct variation provided by y equals a times x, where a does not equal 0. The non-zero number a is called the constant of variation, and y is said to vary directly with x. So, for example, if you have a graph, y equals ax will always go through the origin 0, 0. So direct variation means is as x increases, y increases. So we would say that or describe that as y varying directly with x. So for example, if I give you y equals 5x and then I ask you, is that a direct variation? You would say yes, because it goes through the origin 0, 0. And for 2x minus 3y equals 0, you would have to rewrite it as a function to check. Negative 3y equals negative 2x, and that would equal to y equals 2/3 x. And yes, that's a direct variation. Versus this example to the right, if we write this as a function, y equals x plus 4, we have a y-intercept. This will shift the graph away from the origin. Therefore, the properties of graphs of direct variation equations we could summarize this as follows. The graph of a direct variation equation is a line through the origin 0, 0. The slope of the graph of y equals ax is always a. So you can have a positive slope or a negative slope. Okay, let's practice. Tell whether the equation represents direct variation. If so, identify the constant of variation. I'm going to rewrite y minus 2x equals 0 as a function. Y equals 2x. Yes, this is a direct variation because it follows this model, y equals ax. And our constant of variation would just be 2. For this one, y equals negative 3x minus 2. This is not a direct variation because of this y-intercept. So we just simply say no. And there's no constant of variation. And for this one, 1.3 y equals 6.5x. Y equals 6.5 over 1.3 x, and then y just be 5x. And this would be a direct variation, and our constant of variation would be 5. Part B, graph the direct variation equation. So I'm going to rewrite this as a function. Y equals 5 over 4x, and I know I need to begin at the origin. So remember from the last chapter, to graph using the slope-intercept form, you start at the origin and go 5 units up. 1, 2, 3, 4. Okay, so I'm just going to add another unit up here. 5. And then I'm going to count 4 units to the right. 1, 2, 3, 4. I'm going to stop here. So this point here will be 4, 5. I'm going to connect my points, and I have my graph. And this one, same thing. When we write this in function form, y equals 2.25x, and we're going to begin at the origin. We're going to count 2.25 units up. 1, 2, about here, stop, and then we're going to count 1 unit to the right, because the slope, the constant variation, is 2.25 over 1. I'm going to stop here, so your point will be 1, 2.25, and then we're going to connect the dots. Okay, part C, the graph of a direct variation equation is shown. Write the direct variation equation. Then find the value of y when x equals to 10. Okay, I'm given a point here. And here's the origin. So I can say my slope is -3 over -5, which is 3/5. And I can use the direct variation model, y equals ax. M here is equal to a, so y equals 3/5 x. This would be my direct variation equation. And then I'm going to have to take this equation and substitute 10 into x. Six. Y equals 6. So we have 2 answers. Part D. Tell whether the table represents direct variation. If so, write the direct variation equation. Okay, for the first one, we could just check the slopes. 12, 6. 12 minus 6 is 6. 2 minus 1 is 1. Same thing. 1, 1. 18 minus 12 is 6. As you can see, they're all 6's. So you can say y equals to 6x, and this is a direct variation. And I will have to write the direct variation equation. For the next one, we check -12 minus 6 is -18. -4 minus 8 is -12. And we can find out what that slope is between these 2 points, which is just -18 over -12. It gives you positive 3 over 2. Because if we divide by 6, the top and the bottom. Okay, and we're going to have to check another pair. 96 subtract -4 gives you 100. And 0.5 subtract -12 gives you 12.5. And we can find this slope to be 12.5 over 100, which is 0.125. And this would be 1.5, and they're not equal to each other. So we could stop here and can make a conclusion that these set of points do not form a direct variation. So all you have to say is no. Show your work and write no. Part E. Given that y varies directly with x, use the specified values to write a direct variation equation that relates x and y. So this is not as hard as you think. Just take the direct variation model, y equals ax, Substitute y for 26. Substitute x, 13 for x. Solve for the constant variation, which is 2. And then you can rewrite the direct variation equation as y equals 2x. To use low voltage lighting, you need a transformer to control the flow of electricity. The table shows the size S of the transformer in watts needed for the number N of 12 watts you want to use. Part A. Explain why S varies directly with N. So I'm going to write that as S equal to AN. This part of the sentence simply translates as this. And why do we have to write S here instead of in place of N? It's because as you need more lights, you need bigger transformer sizes. Okay? And if you calculate the ratio, 72 subtract 48 gives you 24. 96 subtract 72 also gives you 24. And the difference of 6 and 4, 2. 8 and 6, 2. And you calculate the ratio to get 24 over 2, which is 12. And part B, it says write a direct variation equation that relates S and N. And the ratio also happens to be your constant variation. Therefore, our direct variation equation would just be S equals to 12N. Part C. How many 12-watt lights can you install using a 225-watt transformer? So remember, this is the size. And the 12-watt light, and how many do we need? Solve for N to get 18 and 9 over 12. Okay, so we cannot count this part because you cannot have half a light. Okay, so we'll cancel it out. So our final answer will be 18 lights. This concludes our lesson.